So how many of you have used OpenStack in your environments, etc.? Okay. A good number of people. And how many of you have heard about OpenStack? Because that's a good number. Okay. So this talk should be of interest to you. Just to raise the curiosity and develop the motivation, does anybody know how many database insert queries and select queries OpenStack, the latest release of OpenStack issues when creating a virtual machine? Can anybody guess any numbers? So, for instance, in the latest release of OpenStack, OpenStack Grizzly, the number of inserts for a single VM create are 37. The number of update queries are about 74. The number of select queries are 137, I believe. A lot. So we're going to talk about how we did this and develop the techniques for that. Okay. So open source cloud projects, there are many of them. This is just a sampling. At various layers, IaaS, PaaS, SaaS. Some obvious ones are probably missing from this picture, like Apache Hadoop, etc. But all these open source projects are evolving at a very rapid pace. Broadly, the open source cloud projects can be divided into two types. One, which are kind of the native projects, which are trying to build a system from scratch. Let's say, OpenStack is providing the IaaS platform, Cloud Foundry is providing the platform as a service, etc. And they are more like the adopter projects, which try to build on top of an existing infrastructure, such as Amazon EC2, Netflix is one of the examples. So these open source projects, this is a quick timeline of the way the OpenStack open source projects I showed. So OpenStack, for instance, was released in the first version roughly in, I believe, July or maybe August 2010 or so. And the important the two important characteristics of these open source cloud projects. One is that mostly they consist of a multi-component distributed architecture. So lots of components talking to each other via REST calls, queuing, database, etc. And they're also characterized by a very rapid development cycle. So what does rapid development look like? Well, for OpenStack, we have got, it is released every 6 months. Some other projects, Eucalyptus and other IaaS, it's every 4 months. You can compare it to some of the other releases, Linux kernel coming out every 2 or 3 months, at least new release. Similarly for Ubuntu distro releases. Now, if you're a cloud provider and if you want to adopt a project like open source, OpenStack, or Cloud Foundry or whatever in your system, you can do a couple of things. You can wait for the new release to come out, but if you are aggressive, which is what some cloud providers are, you can try to adopt code directly from the code trunk into your production system. So the question is, how good is that code, and how much confidence I have in that when I'm deploying stuff, either from a release every 6 months or directly from the code trunk. So just to I guess define this, what do I mean by evolution here? So at a very micro level, evolution can be defined as one level of change that is committed to the code trunk, and obviously at a major level, it is a known release that comes out. So there are at least 3 perspectives when we want to understand the evolution of a open source cloud system, or for that instance, any system. One is obviously the research perspective, that how things are changing across versions or across changes, so that we can say something useful about it. There's also the developer perspective, that once I make some changes into the system, and into a multi-component system like OpenStack, how is that change affecting different components, and how does that change the interaction among different components? And obviously, and lastly, and most importantly, there is the provider perspective. Somebody who wants to deploy OpenStack or or Hadoop or Cloud Foundry to their system, they want to have some confidence in the release before they actually go and deploy. So, there are many different ways of gaining this confidence. Our approach is one of them. I'm not definitely going to claim it is sufficient because there are multiple mechanisms. One can do performance study, one can do end-to-end message tracing, one through debuggers, etc. But some of the techniques that we have developed provide a good, quick, cheap and dirty way to just get more insights about the workings of the system. So, broadly speaking, what are some of the methods for understanding the evolution of a system? Well, for open source systems, there is a source code. One can read the source code, and one can read the documentation. That's kind of more in the static analysis. It doesn't tell us anything about the dynamic behavior of the system. One can also run the system under some control conditions before deploying it into the production. Typically, in cloud providers, we have these dev, test, and production stages. So run in those stages and try to understand the system. And in those dynamic settings, one can look at the system from various vantage points. So one can try to analyze the logs. One can try to understand the end-to-end message flow among different components for logical operations, such as create a virtual machine in OpenStack, or create a web application in Cloud Foundry, or run a Hadoop job, etc. One can do performance benchmarking. One can insert faults, etc. And this can be done in a lab or production environment. So our studies has been focused on leveraging, we have developed techniques to create an end-to-end message flow for OpenStack components. As part of ongoing work, we are enhancing those techniques to insert faults and analyze the robustness of systems like OpenStack. So in particular, what we do is that we do three things. We perform tracing of end-to-end message flow for OpenStack. We, although not presented in this paper, but we have a system almost ready where we can correlate log writes with the message flow, and then we can insert faults at precise points in the message flow to understand the robustness of a system. And we want to do this without source code modification, and that's just one design point. Certainly, by no means, I want to claim that that's the we shouldn't do it. And if it's an open source system, you may just want to augment it with your tracing mechanisms or whatever. But in our case, I'll show you, it provided us, our technique provided us with a quick way of analyzing system without instrumenting any of the source code. There are existing, there are many tracing solutions out there. Google Dapper is one of it, which basically tries to instrument the callbacks between different Google functions, Google systems, and use that to determine or gain insights about the message flow or the interaction between different Google systems. And Twitter has this Zipkin approach, which is an implementation of Dapper, but enhanced. Basically introduce a attach identifiers to messages going across different components of the system to determine how the various requests are performing and where the bottlenecks may be happening. Anyway, so what's the summary of a solution? So as I mentioned, we do tracing, and this is prior art. This work was published earlier, but we have made some significant enhancements to this technique. The basic idea over here is that in a multi-tiered application, such as there's a web server, there's an application server, and then there's a database server. They typically follow certain programming models, and the idea is that if we can correlate their network send and receive calls and thread IDs, etc., then we can, in most circumstances, construct a a perfect path information from the time the request arrives at the web server to how it travels to various components of the system, and a response is sent back. So in this case, once a request arrives, let's say at the web server, so a receive call is made, and then the application, the same thread may send that request to the application server, so we can correlate that receives and sent. Similarly, application server may do some processing, and the same thread may send that request to the database server, which may respond back. Typically, the applications, may operate in two modes. They do an asynchronous send or receive, or they do a synchronous send or receive. But as long as it is the same thread processing the message, we can successfully correlate those sends with the receives, and so construct a perfect path for the application, for the request going to multiple components. Now, that's not certainly the only model for how applications are written. One thing that will break this technique is that if there are queues in the system, so the web server receives some request from a user, and instead of directly sending this to an application server, it would insert this request into a queue, a message queue, which could be anything like a RabbitMQ server or Cupid server, running the well-known MQ paper calls, etc. So the applications, the web server inserts something in the queue, and then does it start doing something, and so the application server will pull this message from the queue. So both are actually pulling some. So one is inserting something in the queue, and the other is pulling, but that insertion of a queue breaks the path information between who is actually pushing the message in the queue and who is receiving that message from the queue, unless of course one augments the message with certain message identifiers, or run, let's say, only one logical operation in the system. Just say we're only testing one create virtual machine operation in the system. So that's for kind of the tracing. How do we do tracing in a system when there may be queues and when there are no queues? And the results I'm going to show here for OpenStack basically you make use of these two techniques. Then we have developed these techniques for correlating logs with the messages. So we can construct a path, but wouldn't it be nice if we can correlate all those send and receive calls? I think I should have mentioned that those send and receive calls are captured using the well-known LD_preload technique. Inject code in the shared library and print it to some files, etc. So wouldn't it be nice if you can correlate those send and receive calls with the log information that's being written, and so that not only we have the flow information, but we also have the log information that the application is generating. And obviously that can result into improved semantics for problem diagnosis. So how would one do that correlation between the message flow and the logs? Well, the idea is pretty simple. Most applications write logs to well-known log files. The log messages or syslog, or in case of OpenStack, they are well-known log names. So if we can augment our tracing mechanism with the information about these well-known log names, so that whenever we detect a write to those log files, we can augment certain information in that write about the message path that the request was going through at that moment. So for instance, in this case, there is a receive, read, and then there is a write. And at that write, we find that this is being written to a particular log. So we can augment certain information, such as what was the file descriptor, what was data error, and maybe some thread and any other request specific information. So we can do tracing, and we can do log correlation with those traced messages. Then finally, we can use this tracing information, the path information, to insert faults at precise points in that path. The idea over here is pretty simple, that we have the end-to-end path. Now we want to have some kind of a language which says that if a regular expression meets certain criteria, or for example, if I receive an HTTP request from this IP address and this port number, do something, kill a process, return -1, whatever. Very precise fault injection. You can also contrast this to high-level fault injection that may be performed using test cases that developers write, but that's one of the techniques that we have. So tracing with log correlation, and then with fault injection, and using these three mechanisms, we can obtain deep understanding about an open source, a distributed open source multi-component system such as OpenStack, understand its robustness, and hopefully try to gain confidence about its operation before we actually go and deploy it in production systems. Okay, so that's kind of the general technique overview. So now OpenStack. OpenStack is evolving at a very rapid rate. From its first release in 2010, with about 30,000 lines of code, it's grown to order of magnitude 10 times in terms of lines of code. So it is being developed at a very rapid pace. In the last release of OpenStack, Grizzly, there were about 500 committers. Mostly, they're committing anywhere between 1 to many lines of code, but that just indicates the number of people who are contributing. OpenStack has a complex architecture. Probably, I'm sure other providers who are not necessarily running on OpenStack but are providing a similar service have such a complex architecture. So OpenStack provides an infrastructure as a service, right? So you can imagine that there has to be some kind of an authentication system. So all the requests coming into the system are authenticated. So they have a system called Keystone. It stores information about the users, their access level, authorization, passwords, etc. Then, in order to provide the infrastructure service, there has to be an image repository. So it provides this notion of image repository using these two services, Glance API and Glance Registry. API server, Glance API is a server that basically receives the image requests from various systems, and registry stores some metadata and it stores it in the database. The physical images themselves can be stored on the file system or potentially anywhere on the internet or wherever one wants it to be. But the image metadata is stored in the Glance database. Then there is the compute controller, which comprises of multiple components. There is the API server. The API server receives requests for creating the virtual machines, etc. And then it authenticates those requests with the keystone, etc. There's the scheduler, which determines on which host the OpenStack is going to launch its virtual machine. Certificate service for providing certificates in OpenStack. A Nova conductor service, which was introduced in Grizzly, which basically took out the database operations from compute nodes and consolidated them into this service, which now runs on the controller node. In the previous releases of OpenStack, that service was each compute node was directly accessing the database. So if you got 1,000 nodes, each of those 1,000 physical nodes are now making direct database accesses. So 1,000 database open connections, potentially a problem. So this figure simply shows the architecture with the quote-unquote virtualized network or software-defined network part of OpenStack. So there's a network controller, which is, an API server, which talks. There's a DHCP server, and then there is a metadata agent, etc. Now, the interesting thing to note over here is that how do these components communicate? So I guess this diagram is probably not the best representation, but the NOVA components, which form the compute controller, they communicate over AMQP, Advanced Message Queuing Protocol, using Rabbit, etc. The components interact with each other through the REST calls, HTTP REST calls. So, NOVA will communicate with Keystone over REST. Glance will communicate with Keystone over REST. As you can see, there are a lot of interactions happening with Keystone because OpenStack is a fully distributed system. So any request that is coming, it has to be authenticated, etc. I'm probably going to skip talking about block storage. And then there is a database operations, a lot of component performing direct database operations, mostly on the controller side. In fact, all on the controller side, nothing on the compute node side. So it's a pretty complex system, as you can imagine. So we wanted to understand the OpenStack data and message flow for logical operations. So in this paper, we talk about our discussed results for creating, deleting a virtual machine and listing virtual machines. And by gathering data about the REST calls, the data flow, AMQP, and timing information, we can do many things: build consistency tool, build some naive data flow models, use them to construct some also naive performance models, etc. Just as part of understanding the evolution and also as part of understanding, gaining confidence about deploying OpenStack in our production systems. So what are some of the key observations for OpenStack? Complexity is brewing under OpenStack. If you look at it, the latest release of OpenStack, Grizzly, it has about 105 tables as compared to 53 in the Diablo release, which I believe was in September 2011. Lots of selects, inserts, updates, etc. We have information about how many tables are touched, about 750 kilobytes of messages of data is read, and half a megabyte is written to across the network for creating a virtual machine. And this data obviously does not include any information. This data does not include the image transfer data, which is separate. Using this kind of flow mechanism, we also gain some interesting insights into the design of the system, which obviously one can gain from reading code, but the flow kind of provided a more quicker way, at least for us. For example, what happens when OpenStack deletes a virtual machine? Are all the records deleted? And we find that there's only one record deleted. All the other records are archived. And if you're an ops person, it kind of makes sense to you. Since OpenStack is multi-component, there has to be some notion of request IDs. So OpenStack does insert some request IDs into its system, and but only after inserting some quota and reservation information in its databases. OpenStack performs this quota management in a very interesting way, and that's, as a system designer, you may like it. So it would insert. So when OpenStack has to create a new virtual machine, it would not go and simply decrement the total available quota, but it would insert an entry into the database indicating that this entry is being reserved, and when the virtual machine is deallocated, it would insert a negative entry so that we have a complete audit trail of what's being inserted, etc. OpenStack has a lot of configuration options. I'm going to show you in a moment that the authentication system Keystone can be configured using token-based authentication or PKI authentication, and there are implications for on the database interaction between these systems. So I'm running out of time. Let me just jump directly into the results. This is a heavy graph, and the way to read this is that we performed analysis for 3 operations. So you'll find on the left number of select queries sent for create, delete VMs and list VMs. So we insert, update, and delete. These are the number of releases we analyzed. For Folsom and Grizzly, we analyzed them both under the so-called quantum, which is their virtualized network or quote-unquote software-defined network setup, and also for their regular networking for the VMs. So note here, I probably don't have enough time to go over all of this, and you can read some of this in the paper, but the number of select requests, for virtual machine creation, pretty huge. Similarly for inserts and updates, etc. So you may ask the question, what is causing those a lot of inserts? That shows that. So these are different OpenStack components, and we saw that for Grizzly Nova network there were about 139 of those queries. So it seems that the keystone component is causing the bulk of the select queries. The other components have pretty low load in terms of selects. And if you correlate those queries with the GET requests or REST calls that a component receives, it provides us a very interesting view. So as you can see that the GET requests, was heavily unoptimized. We tried to optimize in Essex, got a little bit worse in Folsom, and then re-optimized again in the case of Grizzly. So that is somewhat tied to the authentication increase in the authentication select queries. So for Keystone, you can see that it is issuing about 82 select queries for the Grizzly Nova network. But if we were to change the configuration option, we could immediately run our system, this OpenStack, using our tool, and get insights into these number of select queries. So if you run OpenStack under, let's say, if you run OpenStack with this PKI level authentication, the number of select queries drop, etc. There's a lot of other detail. I'll probably skip it in the interest, I guess, time, since I'm running out of time. Just want to point out that this kind of analysis also provides. We saw some interesting behavior of OpenStack, which is these are the number of send or write calls, and these are the number of receive or read calls, and you would expect them to somehow reasonably match, but obviously there's a huge discrepancy over here. And we found that for the REST messages that it was receiving those messages 1 byte at a time, hugely inefficient way, and that's because of one of the use of a particular library. In any case, let me conclude. High-level message, and I was also at the OpenStack Summit, so I mentioned it over there. Also, complexity is brewing under OpenStack. So if you're deploying it in your system, beware. There's a lot of code coming in, and you need to understand the implications of it before you start deploying it in your system, in a real production system. Providing a production level service, or let's say an EC2 equivalent service to your users. The other high-level point, I think, is that for these systems, it is very important to build applications with tracing in mind. OpenStack isn't quite built with tracing in mind, but if you look at some of the big infrastructure projects in some of the large companies, I give you example of Twitter and Google Dapper, they are trying to build their applications with this tracing information, tracing requests, so that they can understand bottlenecks in the system very quickly. Ongoing and future work, we have completed our coding on fault injection and log correlation, and we are also leveraging our tool for some other projects like Cloud Foundry in our system. So with that, I'll conclude, and I'll be happy to take questions.
Can we use your system?
It's not open source, but if you would like to, for example, have a license to use our system, I think that can certainly be discussed.
Is it online? Can I download?
I said it's not open source.
Not open source.
Right.
Hi, it's a great talk. I'm J.K. Lee from H+. The question is, I think the number of SQL queries generated by creating VM, I think it has nothing to do with the size of data center, for example.
Absolutely.
Yeah.
Yeah. So I mean, I should have mentioned it. Number is simply one metric. Obviously, does not say anything about the complexity of the SQL query. The select query may be very complex, have multiple joins, so it may take a minute to run. For the insert queries, we can say with some relative confidence that their time is relatively constant because they are not performing any complex joins, at least the queries we observed. So you're absolutely right. Number is one metric. We don't necessarily show the timing information. The timing information can really be measured when you benchmark the system under some load, and you can leverage our technique, for instance, to measure the precise performance that each query may be experiencing. But this is not a performance study. This is only a tracing study.
Maybe it's not a very good question here, but what if you want to schedule a group of virtual machines, not just one virtual machine? Right. Do you have any kind of high-level insight how it will be complicated compared to the existing mechanism to create a VM, the sequence you showed us?
Right. So I think I mentioned that we have augmented our technique so that we can we augment our technique with the application level information. So the transaction IDs that OpenStack sends across the AMQP, we take into account in creating the flow. So as long as those are taken into account, no matter how many virtual machines you create in parallel, we should be able to construct those flows easily.
Thanks very much for the talk. I thought that was really interesting, and I think that tools such as that is extremely useful to analyzing different software packages. I would love to be able to actually use the tool to do a comparison between OpenStack and CloudStack and Eucalyptus. That's probably not that easily done, is it?
Yeah, indeed. I think we should discuss offline about this. In general, we also want to do comparison with CloudStack and with Eucalyptus and other sources out there to see what's happening and how those things are evolving. But number of people, etc., those kind of considerations.
Yeah. Thanks.
I just have one more quick question. So if you were to pick one surprising fact that you find in your analysis of OpenStack, what would that be, like the most surprising?
Right, I think I mentioned this, the number of received calls, probably it was here. Yeah, I mean, this is just stupid, right? Receiving the messages one byte at a time for those. OpenStack receives those HTTP messages, HTTP responses one byte at a time. It pulls them one byte at a time from the buffer. That's just stupid, I think.